Welcome to Lecture 18. In this lecture, we're going to be talking about the magnetic fields created by current carrying wires. Since we've established that we know there are magnetic fields created by currents, the next thing we want to do is start working towards what is that relationship. If we know the current, how do we find the field? So let's remember that a magnetic field is a vector. We're going to have to be finding magnitudes and directions. Magnetic field has a symbol of an uppercase B and it has units of Teslas, which has a symbol of a capital T. And we're going to try and find the magnetic fields created by some current I. So what do we know about current? We know that current is just moving charges. So let's start by defining the magnetic fields in terms of a charge Q moving with velocity V. That magnetic field is given by the Biot-Savart law. And the Biot-Savart law says that the magnetic field, the vector magnetic field, is mu naught divided by 4 pi times Q times the velocity crossed with r hat divided by r squared. Okay, so there's a lot in this equation. Let's go through each bit. Mu naught is a constant. Remember when we dealt with electric fields, we had epsilon naught. That was the permittivity of free space, and it described how electric fields move through a vacuum. Mu naught is the permeability of free space, and it means how magnetic fields go through a vacuum. So that's our mu naught. Q is the charge that's moving. Something that's important here is that our charge Q can be positive or negative. So it's important to remember that charges can be either way. V is the velocity of charge Q. So we know it's moving. It has a magnitude and a direction. Next, we get to R and R hat. So when we're trying to find the magnetic field, we're trying to find it at some point. I'll just label a point P on my diagram. So let's say we want the magnetic field at point P. R is the vector. So R is a vector that goes from our charge to our point P. So I drew in purple there my vector R. And it starts at the charge Q and it goes to point P. So then R hat is a unit vector, and we've discussed this kind of unit vector before. A unit vector has length of 1, and it has the same direction as the vector R. So if you wish, you can draw that on your diagram. I'll draw that in bright red there. So it has length 1, and it points in exactly the same direction as R hat. So R hat and R have exactly the same direction. So first off, if you want to find the magnetic field, you can just straight up do this equation with the cross product. I kind of assume you're familiar with cross products. I'm going to post a refresher slide on the next slide. I won't go through it, but I am going to post it. If anybody is not certain about this, let me know and we can go through it. So right off the bat, if you want to just carry on finding the magnetic fields by using the equation with the cross product, that's no problem. You can also do it with magnitude and direction, and we'll start to go through that part next. If you prefer not to use the cross product equation to find the magnetic field, then you can find the magnitude using the equation and a right-hand rule to find the direction. Let's go through the magnitude first. So the Biot-Savart law gives the magnetic field as a vector. The magnitude of that magnetic field vector is mu naught over 4 pi, so the constant over 4 pi, times the magnitude of the charge. And I'm putting in the magnitude of the charge here because that can be positive or negative. We're finding the magnitude of the magnetic field, and that's always positive. Then that's times the magnitude of V cross R hat. So that's the magnitude of a vector, cross product, divided by R squared. So one of our properties of a cross product is that the magnitude of the cross product between two vectors, so V cross R hat, is equal to the magnitude of the first vector V times the magnitude of the second vector R hat times sine theta. And pretty important here, Theta is the angle between V and R hat. In vectors, those angles can be a little bit confusing. So let's just put up a reminder there. If we've picked some point P, then we know vector R goes straight from the charge towards point P, and our unit vector R hat is in the same direction as R. So the angle theta we have in our equation is the angle between those two vectors. Make sure you always get that right. Okay, next little thing we might point out, our unit vector R hat has a magnitude of 1. And we'll write that the magnitude of the velocity is the speed v. Okay, let's put all those things together. That means that the magnitude of v cross r hat is v times 1 times sine theta. Okay, let's put that into our equation above. And we get the magnitude of the magnetic field is equal to mu naught over 4 pi times the magnitude of the charge q times v sine theta over r squared. So that's the magnitude of the magnetic field made by charge q moving with velocity v. Next, we have to talk about the direction, and we'll use a right-hand rule to get the direction. To find the direction of any cross product, you can use a right-hand rule. Right-hand rule says you take your right hand and you extend your thumb and your first two fingers as shown in the diagram. Your thumb points in the direction of the first vector of your cross hat in the first vector of your cross product. In this case, that's your velocity. Your index finger points in the direction of your second vector in the cross product. In this case, that's r hat. And then your middle finger is extended. That shows the direction of the resultant. One thing that's important to point out is that the right-hand rule applies to positive charges. So this is a right-hand rule.
I'd like to use my
for
right-hand rule to find the magnetic field due to a charge
If you
plus
had
Q
negative charges, you would still use your right-hand rule, but whatever answer you got in the end,
so
you
I
would
know
just
that
flip
my
it by
magnetic field
180
direction
degrees
is
or
going to be
rotate
given
by
by
180
Q v
degrees.
cross r
Okay,
hat.
so I've got a very quick
Let's
video
remember that
here
r
that
is the
shows how we
vector
would
from
apply
the
the right-hand
charge
rule
to
to
the
find the
point,
direction for the example
and
we've been
r
talking
hat
about.
is the unit vector that points along vector r. So there's my r hat. To apply my right-hand rule, I'm going to put my thumb in my direction of my velocity, which is to the right. I'm going to extend my index finger in the direction of r hat, so up towards P. Then I'll extend my middle finger, and that gives me the direction of the magnetic field at point P. That's out of the page or towards myself. So then I can draw that on my picture. The magnetic field is coming out of the page, so that's a dot inside of a circle, and we'll label it B. So that's how you use the right-hand rule to find the direction of the field.
So now we've got two ways to find the magnetic field. We can straight up do the cross product equation, or we can use the equation and find the magnitude and the right-hand rule and find the direction. Neither way is more correct than the other. You just use whichever one you prefer.